Hey everyone, welcome back for another deep dive. Today we're looking at this really interesting new approach to graph learning.
Yeah, it's a pretty dense paper, though.
It's a beast. This one is called an end-to-end attention-based approach for learning on graphs.
So we're going to try to break it down into some digestible pieces for you.
Exactly. And what's really cool is that this new approach, which they call edge set attention or ESA, it's actually outperforming some of the big names in graph learning in terms of efficiency and accuracy.
Yeah, it's kind of like the underdog story.
I love those. So let's start with the basics. What is graph learning and why is it such a big deal?
So graph learning is essentially teaching computers to make sense of data that's structured like a network.
I can think of like a social network or something.
Yeah, exactly.
Yeah.
Social networks or the connections between atoms in a molecule or even like the internet itself. It's all about understanding relationships.
So it's like teaching a computer to read a map of connections. Exactly. And by understanding those connections, computers can do some really powerful things like predict your next favorite song on Spotify.
Or help scientists discover new drugs.
Exactly. The problem is that traditional methods for doing this, like graph neural networks or GNNs, they could be really computationally demanding.
And they often struggle with these like long-range connections within the data.
Yeah,
Yeah.
exactly. It's like they can see the trees, but not the whole forest.
So that's where ESA comes in.
Right. ESA seems to address some of those limitations. And what's unique about it is that it focuses on the edges of the graph.
The edges, so the connections themselves rather than the nodes or the individual data points.
Exactly. And that shift in perspective really allows ESA to hone in on the relationships within the data.
It's like it's looking at the roads instead of just the cities.
Yeah, that's a
Yeah.
good way to put it. And to do this, it uses this really cool concept called attention.
Okay, I've heard of attention before, like with those big language models.
Yeah, it's a similar idea.
Yeah.
Here it's about focusing on the most relevant information.
So like when I'm reading a book, I don't pay attention to every single word. I focus on the key phrases and the sentences that convey the meaning.
Right, and attention in graph learning is kind of like that. It helps the model zero in on the most important connections within the data.
Okay, that makes sense, but I'm still a little fuzzy on how ESA actually uses attention to process information about these connections, what's going on under the hood.
So ESA utilizes two main types of attention. There's masked attention and self-attention.
Okay, let's start with masked attention. What is that?
So imagine you have this graph and you place a mask over it. You're blocking out certain connections and allowing the model to focus only on specific relationships.
So it's like giving the model blinders so it doesn't get distracted.
Exactly. And that helps it really concentrate on the connections that matter most.
That's cool. And then what about self-attention? How does that work?
Self-attention is all about understanding each connection within the context of all the other connections in the graph.
So it's like being able to see the whole forest instead of just individual trees.
Precisely. And by combining these two types of attention, ESA is able to gain a really deep understanding of the relationships within the data.
So it sounds like a pretty powerful combination.
Yeah.
But does it actually work? Does ESA actually outperform the more established methods?
Yeah, that's the amazing part. It really does. And in some cases, quite significantly.
Yeah.
Not only does it beat traditional GNNs, but it's actually surpassing some of those more advanced graph transformer models as well.
Wow, that's impressive. And we're talking about across a whole range of tasks and data sets, not just like one specific thing.
Right. It's been tested on a variety of benchmarks, and it's consistently performing at the top of the pack.
Okay, I'm always a sucker for specifics. So
Yeah.
give me a real world example where ESA really shines.
Okay, so let's look at PCQM4MV2, which is this massive data set used to predict the properties of molecules.
Molecules, like in chemistry.
Exactly. You know how important it is to understand how a molecule is going to behave for things like drug development, right?
Right, so being able to predict those properties accurately could really speed up the process of discovering new medications.
Exactly. And the top performers on this data set, highly specialized models designed just for molecules, were really struggling to get below a prediction error of 0.067.
Okay, I'm going to need a little help understanding what that number actually means.
Yeah.
What does a 0.067 error mean in this context?
It's essentially a measure of how far off the model's predictions are from the actual values.
Mm-hmm.
So the lower the error, the better.
Okay, so lower is good. Got it.
And what's remarkable is that ESA, this general purpose model, achieved an error of just 0.0235 on the same task.
Wow, that's almost 3 times lower.
Right. And it was able to do this while using a much simpler architecture than some of its competitors.
So simpler and more accurate. That's pretty amazing. It's fascinating to see a general approach like this, outperforming models that were specifically designed for that particular task.
Yeah, it really highlights the power of ESA's approach.
It suggests that it's picking up on some like fundamental patterns within the data that are applicable across different domains.
Exactly. And this wasn't just a fluke either. ESA has also proven its dominance with molecular property prediction in another test, the QM9 dataset.
Okay, what is QM9?
It's considered like the gold standard in the field.
Yeah.
And ESA outperformed the competition on 15 out of 19 properties.
15 out of 19, that's pretty convincing.
Right. It's a clear sign of its robust capabilities.
So it's accurate, but is it also efficient? Because we talked earlier about how some of those traditional methods can be really computationally demanding.
That's where things get even more interesting. ESA is not only accurate, but it's also incredibly efficient. It uses less memory and trains faster than many GNNs and some graph transformers.
So it's like getting better results in less time. That's a win-win for sure.
Exactly. And part of this efficiency comes from the fact that ESA is really well designed. It doesn't require all the complicated pre-processing steps that some other models need.
So it's kind of like a minimalist, cutting through the clutter to get to the core of the problem.
Yeah, that's a great way to think about it. And the research team is actually continuing to explore ways to make ESA even more efficient. They're looking at integrating advanced techniques like flash attention, which has already shown it can significantly speed up training times.
So ESA is accurate, it's efficient. It sounds like there are some pretty exciting applications on the horizon.
You're absolutely right. But before we get to those, I want to highlight another really important aspect of ESA. It's its ability to capture long-range interactions within the graph.
We touched on that a bit earlier, but I'm curious to hear more about why this is such a big deal. Why do those long-range connections matter so much?
So think about a social network again. A direct connection between two people is pretty easy to analyze. But what about the indirect influences that flow through multiple connections?
Oh, I see. What about like how information spreads through a network or how opinions form? Those things are influenced by much more than just who you're directly connected to.
Exactly. And those indirect influences are often much harder to capture, but they can have a huge impact on how a network behaves.
It's like the difference between hearing something directly from a friend versus hearing it through the grapevine. The source and the path the information takes can really change its meaning.
Exactly. And ESA, with its attention mechanisms, is remarkably good at capturing and processing information from those more distant connections within the graph.
It's like ESA has a sixth sense for those hidden influences that ripple through a network. That's pretty cool.
And this strength makes it particularly valuable for tasks like analyzing social networks, understanding protein folding, or predicting the spread of diseases, all scenarios where those indirect connections can be really crucial.
So we've talked about ESA's unique focus on edges, its use of attention, its impressive accuracy and efficiency, and its ability to handle those tricky long-range interactions. What else makes ESA stand out? What haven't we covered yet?
There's one more really crucial detail that really sets ESA apart. It's the way it combines those two types of attention we discussed earlier, masked and self-attention, into an interleaved structure.
Okay, I'm picturing like layers of masked and self-attention stacked on top of each other. What's so special about interleaving them in this way?
It's all about creating this balance between local and global understanding. So those masked attention layers, they provide a strong foundation by focusing on the specific relationships defined by the graph structure.
Okay, so like learning the basic rules of the game.
Right, and then the self-attention layers come in and they broaden the context, allowing the model to pick up on more nuanced patterns and connections.
So then it's like figuring out all the clever strategies you can use within those rules.
Exactly. And this back and forth between focused attention and broader context seems to be a key ingredient in ESA's success.
Interesting. So it's not just about using attention, it's about using it in a clever and strategic way. The whole is greater than the sum of its parts.
Right. Speaking of the whole, where do you see this research going next? What jumps out at you as the most significant aspect of ESA so far?
You know, honestly, before we started this deep dive, I kind of thought of graph learning as this like niche area of AI, something that only specialists really needed to understand.
Yeah, I get that.
But now I see just how fundamental it is and how much potential it has for impacting so many different fields. And what's really blowing my mind is that ESA achieves these incredible results with a relatively simple and elegant approach.
It is pretty elegant, isn't it? And you're right, it highlights how powerful it can be to strip away complexity and focus on the essential elements of a problem.
And in this case, that essential element is the relationship, the connection, which is relevant to pretty much everything in our world.
Yeah, you got it.
I'm really curious to hear more about how ESA is being applied to specific problems and what kind of breakthroughs it might lead to.
Well, that's exactly where we're headed next. Let's dive into some of the areas where ESA is already making waves and explore the exciting possibilities it's opening up for the future.
Sounds good. Let's do it.
So we've laid the groundwork for understanding ESA. And you're right, its potential applications are vast. Let's start with an area where it's already showing remarkable promise. Drug discovery.
Okay, drug discovery. So how is ESA being used to speed up the search for new medications?
One of the key challenges in drug discovery is figuring out which molecules are likely to be effective against a specific disease target.
Right, because you need to find the right molecule that will actually bind to the target and do what it's supposed to do.
Exactly. And this often involves a process called molecular docking, where scientists try to predict how well a potential drug molecule will bind to a target protein.
It's like a matchmaking service for molecules.
Exactly. You got to find the perfect fit.
Yeah.
And ESA has proven to be quite adept at this matchmaking game. In tests using the docstring dataset, ESA outperformed all other methods, including highly specialized GNNs, on 4 out of 5 targets.
So it's beating out those models that were specifically designed for this task.
It is. And what's even more remarkable is that ESA achieved this level of accuracy while using a much simpler architecture than some of its competitors.
Simpler and more accurate. Okay, I like where this is going. But drug molecules are relatively small and well-defined. Can ESA handle larger, more complex biological structures?
Absolutely. We also tested ESA on peptides, which are chains of amino acids that play really critical roles in biological systems.
Right, peptides. So these are much larger than the small drug-like molecules we were just talking about.
Yeah, much larger. Analyzing them presents a unique challenge, especially when it comes to capturing those long-range interactions.
I'm guessing that ESA's ability to handle long-range connections really came in handy here.
You're absolutely right. We tested ESA on 2 challenging peptide benchmarks. Peptide Struct, which focuses on predicting the 3D structure of a peptide, and Peptides Func, which aims to predict its biological function.
Okay, so 2 different tasks, both focused on understanding these complex peptide structures.
Right? On the Peptide Struct benchmark, ESA achieved a lower error rate than highly optimized graph transformer models while using only half the number of layers.
So not only is it getting it right,
Mm-hmm.
it's doing so with remarkable efficiency. It seems like ESA is really well suited for tackling these complex problems in bioinformatics and computational biology. Are there other areas where it's exceeding expectations?
Oh yeah, definitely. It's making waves in the analysis of software too.
Software, okay, that's a bit of a jump. How does that work?
So we tested ESA on the Melnetny dataset,
Mhm.
which is made up of function call graphs.
Function call graphs, I'm not familiar with those.
It's basically a map of how different parts of a program interact with each other.
Okay, so like a network of functions within a piece of software.
Exactly. And once again, ESA achieved the highest recorded accuracy, even surpassing specialized graph transformer models.
It's fascinating to see how ESA is proving its versatility across such diverse domains. From predicting the properties of molecules to analyzing the structure of software, it seems like it's finding those hidden connections that drive complex systems. But so far, we've been focusing on tasks that analyze the entire graph as a whole. What about tasks that require understanding individual data points within the graph?
That's a great question. And it brings us to an important point. While ESA excels at these graph-level tasks, it did face some challenges when we tried to apply it directly to node-level tasks.
Node-level tasks, so tasks that involve predicting properties or classifications for individual nodes.
Exactly.
So while ESA can see the forest, it was having trouble identifying specific trees.
That's a great analogy, and this limitation kind of stems from the fact that ESA primarily focuses on learning representations for edges, those connections between data points.
Okay, so it's really good at understanding the relationships, but it doesn't necessarily have a direct way to translate that information into predictions about individual nodes.
Right? It's like having a detailed map of the roads, but no labels for the cities.
I see. So how did you address this challenge?
Initially, we tried adding an extra component to ESA called an edge-to-node pooling module.
Okay, so this module was designed to take those edge-based representations and turn them into node-level embeddings.
Exactly. We were essentially trying to give ESA a way to zoom in from the connections to the individual data points.
Did it work?
It showed some promise, but it also introduced a computational bottleneck that made it difficult to scale ESA to really large data sets with millions of edges.
Ah, so even ESA has its limits.
It does, but we didn't give up. We also explored a simpler approach called node set attention, or NSA.
Node set attention. So instead of focusing on the edges, you shifted the focus back to the nodes themselves.
We did. And NSA actually uses the same attention mechanisms as ESA.
Okay, so it's applying those mask attention and self-attention ideas directly to the nodes.
Exactly. It allows the model to learn representations for individual nodes based on their relationships with other nodes.
So you essentially adapted ESA's core principles to work at the node level.
Exactly. We wanted to see if this simpler formulation could effectively handle those node-level tasks without sacrificing the benefits of attention.
And what were the results? Did NSA live up to expectations?
We were really pleased with how it performed. We tested it on a variety of benchmark datasets, including classic citation networks like Quora and CiteSeer.
Citation networks, so like networks of academic papers where the connections represent citations between papers.
Exactly. It's a very common benchmark.
Yeah.
But we also wanted to see how NSA handled heterophily.
Heterophily. For our listeners who might not be familiar with that term, can you give an example of what that means in a real-world network?
So imagine a social network where people with very different interests or political views are still connected.
Okay, so like people who might not be very similar to each other, but are still linked in some way.
Exactly. That's a classic example of heterophily.
Hmm.
And traditional GNNs often struggle with this because they tend to assume that connected nodes are similar.
So they make assumptions based on proximity rather than actual content or characteristics.
Right. But ESA, with its focus on attention, doesn't make that assumption, which gives it an advantage in these more complex scenarios.
So how did NSA, with its node-centric approach, handle those heterophilous networks?
It actually performed exceptionally well. NSA achieved the highest accuracy on both homophilous and heterophilous graphs, outperforming both traditional GNNs and graph transformer models.
So whether you're focusing on edges with ESA or nodes with NSA, it seems like attention is the key. It's consistently proving its ability to learn and generalize effectively from this complex graph data, even when those connections are messy and non-obvious.
Yeah, it really highlights the power of attention as a core mechanism for graph learning.
It seems clear that ESA in both its forms is a significant advancement in this field.
I agree. And what's even more exciting is that this is really just the beginning. ESA is still in its early stages of development, and researchers are already exploring all sorts of extensions and applications.
Okay, I'm eager to hear about those. What are some of the cutting-edge developments that have you particularly excited about the future of ESA?
So there are a lot of directions this research could go next, but one area that I'm really excited about is the development of more specialized masking operators.
Masking operators. So you're talking about those masks that help ESA focus on the most important connections.
Exactly. Researchers are now experimenting with designing masks that are tailor-made for specific types of relationships and data.
I remember you mentioned like tailoring masks to different types of social connections, like friendships versus professional relationships.
Right. So instead of treating all connections equally, we could design masks that differentiate between strong ties like close friends and weak ties like acquaintances.
So ESA could learn that information might spread differently depending on the type of relationship between two people.
Exactly. And by incorporating that understanding of social dynamics, ESA could make much more accurate predictions about how information flows through a network, or how communities form, or even how influence spreads.
So it's about giving ESA a deeper understanding of the context of those connections, not just treating them as abstract links.
Precisely. And this idea of specialized masks can be applied to other domains as well. Imagine designing masks that represent different types of chemical bonds and molecules.
Or different types of roads and traffic patterns in a transportation network.
Exactly. It's like giving ESA a set of specialized lenses to view the world through, each one tailored to a specific type of problem.
That's a great analogy. So this line of research has the potential to significantly improve ESA's performance and unlock new applications in all sorts of fields.
Absolutely. And speaking of exciting explorations, another area that I think holds a lot of promise is combining ESA with other machine learning techniques.
We've talked a bit about that already, but I'm curious to hear more about the specific combinations that have you most excited.
One area that's particularly promising is integrating ESA with natural language processing, or NLP.
NLP. So imagine being able to analyze not just the structure of a social network, but also the content of the messages being exchanged.
Exactly. That would allow ESA to gain a much deeper understanding of the sentiments, opinions, and topics being discussed within a network.
So you could track the spread of misinformation or identify emerging trends or even predict how people will react to certain events.
Exactly. And this isn't just limited to social media. Think about scientific papers, legal documents, or even customer reviews.
So by analyzing the text and the relationships between documents, ESA could help us identify promising research directions, predict case outcomes, or even understand market trends.
Right. It's like giving ESA a way to read between the lines, to understand not just the literal words, but also the underlying meaning and context.
And then what about combining ESA with image recognition?
Oh, yeah. That's a really interesting one, too. Imagine a scene with multiple objects, like a busy street corner.
Okay, I'm picturing it.
We can represent the relationships between those objects as a graph, and then feed both the image and the graph to ESA.
So ESA could learn not only what the objects are, but also how they relate to each other within the context of the scene.
Exactly. It could learn that a car is likely to be on the road, or that a pedestrian is probably walking on the sidewalk.
That would be really valuable for things like self-driving cars.
Right.
Yeah.
Absolutely. They need to understand not just what they're seeing, but also how those objects are likely to behave based on their relationships within the environment.
This is really blowing my mind. It's amazing to think about all the ways ESA could be used to analyze different types of data, both individually and in combination. It feels like we're moving towards this more holistic understanding of the world, one that recognizes the interconnectedness of everything.
I think you've hit the nail on the head. Traditionally, data analysis is often focused on isolating individual data points and studying them in isolation.
Right, like looking at things in a vacuum.
Exactly. But with ESA, we're shifting our focus to the relationships between those data points,
Right.
to the connections that give them meaning and context.
It's like we're finally acknowledging that the whole is greater than the sum of its parts.
Precisely. And this shift in perspective has the potential to unlock entirely new insights and discoveries. It could help us understand complex systems in a much deeper way, revealing hidden patterns, connections, and influences that were previously obscured.
It's like we're putting on a new pair of glasses
Mm,
that allows us to see the invisible connections that shape our world.
I love that analogy.
Yeah.
And as ESA continues to evolve and mature, I believe it will become an indispensable tool for anyone seeking to understand the intricate web of relationships that defines our world.
This has been an incredible deep dive into the world of ESA. It's definitely opened my eyes to the power of graph learning and the potential it has to transform so many different fields.
I'm so glad to hear that. I hope our listeners are feeling inspired as well.
So to wrap things up, let's leave our listeners with one final thought to ponder. We've talked about how ESA can be used to analyze existing graphs, but what about its potential for designing new ones?
Ooh, that's a good one.
Could we use ESA to optimize the structure of a social network to promote positive interactions? Or to create a transportation network that minimizes congestion? Or even to design new molecules with specific properties?
Those are fantastic questions. It's like shifting from reading the map to becoming the cartographer, using ESA to shape the very structure of the networks we inhabit.
Exactly. And I think that's where the true power of ESA lies. It's not just a tool for understanding the world as it is, but a tool for shaping the world we want to create.
Well said.
This has been such a thought-provoking conversation. I'm really excited to see what the future holds for ESA and for the field of graph learning as a whole.
Me too. Thanks for joining us on this deep dive into the world of ESA. We hope you enjoyed it.
And who knows, maybe you'll be the one to make the next groundbreaking discovery in this exciting field. Until next time, keep exploring and stay connected.